problem you have multiple parameters. In other words, we introduce, so you have, case one is where you have just one unknown. Let's say one angle of arrival in your case. So the case two is, suppose there are two sources and two angles, two unknowns, same data set. So we try to estimate both of them. The question is the introduction of a new unknown, how does it affect the error on the first unknown? Will it increase, decrease, stay the same? Anyone? If you have more unknowns, what happens? Is it what happens to the variance of the first unknown? Huh? Increase or decrease?
Increase.
What? Remember, you have a situation where there were only one unknown. Now you note a second unknown, third unknown, etc. comes into the data set, and you do the unbiased estimation for each of them separately. And then one measure is the Cramer Rao bound for each of them. So the first situation A is only one unknown. Situation B, multiple unknowns. Still the first unknown is the same, but then you have other unknowns. So what happens to the variance or equivalently the Cramer Rao bound for the first unknown? Huh? Remember, you have made the scene more complicated. There are more unknowns.
Well, at least for the last example, it was the same, right?
What is the last example?
Mu and sigma, where mu and sigma both were unknown. It didn't change, like estimating.
Oh, it didn't change. It did change. It didn't change for mu, but it changed for sigma squared, isn't it?
The Cramer Rao one stayed the same.
First unknown is the same, and yeah. So, but that's only one example. So, in general, we would expect that once you introduce, like common sense would say, once you introduce more unknowns, it can't get better, right? It can get worse. So we want to look at that situation, right? It can get worse. I mean, I know you're showing an example where it didn't get worse, but you can't go to the other extreme, right? Saying that it would get. So you have, and we'll take the general case. You have multiple unknown parameters. So we'll have a little bit of matrix theory. So again, the same data set, x1, x2, etc., xn. Let's say IID, or it doesn't have to be, but. And so you have the joint density function of all the data points. And I'm going to call theta to represent this vector. So in this case, we will have, let TIX be an unbiased estimator for theta I. So T1, T2, etc. are the unbiased estimators for theta 1, theta 2, etc., theta k. Remember, so this is very similar to the problems you guys work on. There are a number of sources are coming at you, data sources. So in general, this will be also unknown. But let's say you know the number, then there will be, this could be the angles of arrival, literally, sources. And so from the data, you come up with one way or the other way, or even this is very hard, getting generally unbiased estimators. But let's say we have unbiased estimators, and then you have their variances, right? So anybody, what does the Cramer Rao bound say in this case? Anyone? What is the, so you can say the variance is greater than or equal to what? Except how will you find out the what is the Cramer Rao bound here?
Theoretical log likelihood of only theta 1 or theta.
Yeah, but remember that's not the problem. So we have to deal with the problem we have. So this is, you can see all these unknowns are simultaneously present. So all we have access to is this joined density function of the data. It's already a function of all of them. You can't eliminate this. You can eliminate these random variables by integration if that's what you're trying to say. So in this case, what happens is you can of course do the, so we will assume that the regularity conditions are true with respect to any one of these parameters. Okay, in other words, for example, the derivative of the density function is the same as etc. for any one of these parameters. Equal to 0, etc. So we'll assume the regular. So the question is, we want to find this out, how the additional parameters. So you can see there are k estimators. They are random variables. So because we are dealing with the same mixed problem, it's natural to assume that these estimators will be correlated. So you have to look at their covariance matrix. So the covariance matrix of Tx, so let me define T first. T of x is this T1 minus theta 1, T2x minus theta 2, or you can simply define it to be, remember these are the unbiased estimators for theta. So let me define theta to be the column vector of, so theta is this vector. So the covariance matrix, I don't know whether you remember this. This is going to be T of x minus theta. So this is a vector, this is a column vector multiplied by its transpose, T of x minus theta transpose. Okay. I mean, in the real case, otherwise this will be complex conjugate, etc. So this will be a k by k vector, I mean k by k matrix with the, so if I call this to be Rij, R matrix, so it's Ij, if I call this to be an R matrix, covariance matrix, then Rij would be expected value from here. Tix minus theta I multiplied by Tjx minus multiplied by theta j. So that's the cross covariance between the ith estimator and the jth estimator. And what will be the diagonal entries? Anybody? Rii will be expected value of Tix minus theta I, the whole square. So that's what we are interested in. These are the variances of Tix. We want to get a bound on this. See, this is what we are interested in, the variance of the Tix. That will be along these entries. Okay. And this is a non-negative covariance matrix, as you know, is always a non-negative matrix because it's a vector multiplied by vector transpose, right? So let me also define, again, motivated from the Cramer Rao bound for the single parameter case, I can see we have the logarithm of all the data sets, right? So I can take the derivative with respect to any one of these parameters, right? Theta 1, theta 2, etc. I equal to 1 through k, right? K parameters. And remember these functions, so let me define a vector to be d log f. F is this joint density function with respect to theta 1, d log f with respect to theta 2, etc. d log f with respect to theta k. I put f just to show that the Fisher, so this is a random vector because this is a function of the x's. So we can look at the expected value of f, or instead of f, let me call this y. Yeah, that's fine. So this is also a non-negative definite matrix, right? Any random vector multiplied by its transpose, expected value is a non-negative. In fact, we will assume it to be a positive definite matrix. And this I'm going to call it as this one, J. And I'm going to give it a name. So this J is, I'm going to assume that the density function and the parameters are such that J is non-negative definite. I hope you see why J is, because if you take any other vector C and do J, C star J, so etc. This is C is expected value of F transpose multiplied by C. But then Z is any arbitrary vector, not random. So bring it inside, then you can write this as C star F multiplied by F star Z. So you can see the whole thing, you can write it as, this is a standard procedure, Z star F the whole squared. F is random, but this will be some inner product, random variable, but being square, this will be always a positive quantity. That's how you prove the positive definiteness of J. So J is a positive definite matrix. Any questions?
It should be positive semi-definite, right?
Well,
if greater than or equal to 0.
Right, but we are going to assume that the density function is such that with respect to parameters, that it is actually, in general you are right, it could be, the covariance matrix of any random vector could be non-negative, could be in general, of course it will be non-negative definite.
Can you assume the rank is equal to K of
Huh?
the matrix F?
Yeah, of course, the rank is equal to not F. F is a random vector. What matters is J. That's where all the information is. So let's look at what is Jij, the ith and j. So that's the expected value of d log f with respect to theta I, d log f with respect to theta j. So these quantities, remember J is like this. So this matrix is like this, J11, J12, J1k, J21. So our assumption is the data and the density functions are such that this is a positive definite matrix. And the ijth entry is, so look at the ith entries. So for example, the ii entry would be, I and j would be the same. So here you have d log f by d, what we have done the first time, right? So if you only have one entry, this is just going to be the Cramer Rao entry. Remember, expected value. And this is a positive quantity because there's a square here. So why am I doing this? So I have Tx and I have the J. Now let me so let's look at this fundamental equation. So let's expand this. This is going to be what? integral Ti x minus theta I multiplied by d log f by theta j. So that's going to dx, right? Depending on the multiple integrals. So I have two integrals, right? Tx minus tx. This expected value, so multiplied by f, of course, right? So let me expand this. So this is going to be Tx d log f over d theta j fx minus theta I goes outside if you want, d log f over d theta j f dx. We'll use the regularity conditions. Before that, if you want, you can write one more stuff. D log f by d theta j, I'm just going to rewrite it here. It's going to be 1 over f multiplied by df over d theta j. And the same thing here, right? So 1 over f multiplied by df over d theta j. Now f cancels. And now we can use the regularity condition. So this goes in outside, so d theta j. And this was Ti, right? So this is Tix dfx dx minus, look at here, the regularity condition, this is 0 because this derivative goes outside. So this is minus theta I d by dj of the area under a density function, which is 1. So this whole thing is 0. So you will get, whereas this being an unbiased estimator, this is the expected value of Ti. That is theta I. So you have the partial derivative of theta I with respect to theta j. So what I want to say is you get this result. This is 1 when j is equal to I. This is 0 when j is not equal to I. All right, so we have these two matrices. So let me show you. Let's look at okay, what is it? Any questions? Yeah. So this is T1 minus theta 1, theta 2, theta k. So these are 0 mean, right? T. So now let me define Z or something to be, let me put one vector below the other. So remember, this is a k by 1 vector. This is k by 1. So Z is 2k by 1. I'm going to look at Z is again a random vector because T is random, F is random. So we'll look at the, both are 0 mean, right? This is 0 mean.
Is Z T or I?
Huh?
Is that I or is that?
What is this now? This is T and F. T is here. This vector. What is the expected value of here? Vector, right? So what is the expected value of f? Anybody? Expected value of t is 0 because these are all unbiased estimators. Look, expected value means what? We went through this, right? Regularity conditions, because expected value of the first term, which is multiplied by the density function. So this is 1 over f df by d theta 1 multiplied by f. F cancels. Derivative goes outside, it is 0. So f is also 0. So if you look at the covariance matrix of Z, covariance matrix of Z is simply expected value of Z transpose. Yes, because the mean is 0. Mean of Z is 0. So from here, mean of expected value of Z is 0. So that's the covariance matrix is non-negative definite. But now let's look at the covariance matrix of Z. So that's going to be TF multiplied by T transpose F transpose. So that's going to be expected value of TT transpose yeah. And anyone, we already have results for TF transpose. This is going to be a matrix. This is, look at here. So this is the ijth entry of, so if I call this matrix to be A, and A transpose, this is Aij here, right? This is Aij. So as you said, Aij is 1 only when I equal to j. So I hope you see that this is where I want to start. I hope you see that I transpose is I. So this is my identity matrix, right? And this is, I'm going to assume that this is non-negative definite. All right, so what? So look at your matrix. You have this matrix is of this form, right? A, B, B, D. A, B, B, D. And B is the same as B transpose. So let me just multiply, remember, we don't even need B, this is simple, here B is I. So let me just multiply this with this matrix. B is I. So what do you get? Anybody? We'll do it directly. So first row into first column, what do you get? A minus? Yeah, the Laplace rule, right? Minus D inverse. First row into second column. And second row into first column. I also. And second row into second column. What?
Second row first column.
I, right? I multiple the, my second row into Right. Why did you say I? So look, first row into second. First row into second column is I, okay. Second row into first column, look at here, I minus I, which will be 0, right? Okay, now I'm going to call whatever is this matrix, I'm going to multiply by its transpose here. Because remember, this is a covariance matrix, here, this whole thing, covariance of Z. And so let's look at it. So what is the transpose? The row becomes the columns becomes the row. So minus D transpose inverse and identity. Remember, D is, in your case, D is already J is the same as J transpose because J is already symmetric. So your D also is symmetric. So this becomes simply D inverse. Okay. So again, so we just need to multiply here I minus D inverse. This is not I minus D inverse, but D minus D inverse, then 0 I. So first row into, so what do you get? A minus D inverse. First row into second column, what do you get? 0. Second row into first column, 0. And second row into, so you get D. So this is non-negative definite because look, this is a simple result, right? I think you know that. If R is positive definite, S transpose RS is positive definite. That's the result I want to use. So what is the conclusion here? See, from here you can't conclude, you can conclude, but here you can conclude that this submatrix must be non-negative definite because that's another result of a positive definite matrix. Every principal minor, which is this, so this is non-negative definite, this is non-negative definite, this is non-negative definite, the whole thing is non-negative definite. So what we have is, what did we have here before? A minus D inverse, 0, 0, D. So we know that this is non-negative definite, which we already knew. So this is non-negative definite, this is non-negative definite, but now we have, through this transformation, A minus D inverse is non-negative definite. So A is what? So we have covariance of T minus J inverse is non-negative definite, which is the same as saying that covariance of T I showed you earlier, these are covariance of Ti, Tj. These are the entries. Minus, this is J11, J12X. So J inverse, this is a standard notation, right? If J has entries, J, Ij in the denominator, or subscripts, J inverse, you can, generally people write it like this, superscript. So look here, you can read the diagonal entries. Variance of the first one is greater than not 1 over J11, but you have to take the J matrix, takes the inverse, then the first entry. So the Cramer Rao bound for the, when you have multiple parameters, so the question was here. So the answer is here. Because variance of T2 is greater than or equal to J22. So you know the procedure, right? So the procedure is you find the J. So J is this Fisher information matrix whose ijth entry is Jij. So Jij is, what is it? We went through this, right? Expected value of d log f with respect to theta I, d log f with respect to theta j. And then you take the inverse and you call that one to be, you put it this way. Then the variance for the first one is so let's say there is one unknown here. So here, because there are k parameters, rest of them are known. So variance of T1 hat is, because J11 is what? Expected value of, look at that, d log f d theta 1. This is your old result, what we learned 2 weeks back. And here, the same problem, but you have more unknowns, then it says variance of T1 is greater than or equal to J1. So anybody, you have two bounds here. One is when the other parameters are known, whether when the other parameters are unknown. In terms of the bound, so it is two different problems. So but in terms of the bound, which one do you expect to be worse?
Second.
So can you show that this bound is worse than this? Anyone? So this must be a standard matrix results. Look at what we are dealing with. We are dealing with a positive definite matrix. And in fact, this is true. You should be able to show that for any positive definite matrix, 1 over the diagonal, any diagonal entry is, or if you take the inverse of the matrix and take the corresponding diagonal entry, you're saying which one is greater between these two? Which one is greater? This one is greater, right? So you should be able to see whether you have enough skills to show that this is always true. This is always true, but the question is, how do you show this? A couple of ways you can show this, but let me show it for a 2 by 2 case. That's easy. So we'll do 2 parameters. Then you can actually quantify the degradation due to parameter, second parameter, etc. So 2 parameter case. So J is what? J is just J11, J12, J12, J22. Because you can see these two are exactly the same things, right? J, right? J11 is what? Expected value of d log f d theta 1 squared. J12 is expected value of d log f d theta 1. So you just have to do it for each. This you can do for the Gaussian case. And this is again a standard result. You can find out the results. But I'm writing for any general problem. And this is a positive definite matrix. That's our assumption. Otherwise you cannot take the, now we need to take the inverse. Anybody? What is the inverse of this? 1 over the determinant. What's the determinant? Right? Multiplied by, what is the inverse? Anyone? Anybody remember? And? So the, yeah, negative, right? So this is J11, J12. So you can see J11, for example, is J22 divided by J11. So I'm going to cancel, divide by J22 and then pull out J11. Yes, this is true, or yes or no? And this quantity is, this, if I call this to be epsilon, we know epsilon is less than 1. Why? Anybody? Not covariance. This, what is the determinant is? Positive. That means this term is greater than this because it's a positive definite matrix. So this is less than 1. So 1 minus something less than 1 is less than 1. 1 over that is blow up. So this quantity is multiplied by a quantity which is greater than 1. So this quantity, you know, is greater than 1 over J1. But I want you to do this for general case. So general case also you can prove it like this. For example, if you write like this, you can find the determinant, but then you have to do the cofactors and this and that. The easiest way is you do the eigen decomposition of J, and then J would come out to be arithmetic mean. The inverse, the ith entry of the inverse matrix would turn out to be harmonic mean, and then you can use that relation to show this. But here I hope you see this. So we have, in this case at least, yes, because this whole factor is greater than 1, right? This has to be positive because J11 is positive. So this factor has to be less than 1 and positive, right? Of course it is positive. So 1 minus something less than 1 is even less than 1. Inverted that this quantity is greater than 1. So you are multiplying by a quantity greater than 1. So this is greater than this. And so if you want to know what is the degradation, you can look at, so this factor which is positive will give you the degradation of, in the Cramer Rao bound by bringing in a second unknown. And what happens if finally what happens if this Fisher information matrix turns out to be diagonal? Anybody? That means the second parameter is not going to affect the first parameter. So in design of experiments, if you have freedom to choose, you want to design things so that the Fisher information matrix turns out to be diagonal. If you have freedom to, if your design parameter comes in here, then you can adjust it so that these terms are 0, etc.
That is the only case when